Welcome to our online chemistry class. Our topic is transition and inner transition element. First of all, we'll discuss the transition elements. So transition elements belongs to D block of the periodic table. For that purpose, we will see the modern periodic table. So here from group number 3rd to group number 12 and from period number 4th to 7th, the elements are placed in modern periodic table. They are D block elements. So as per IUPAC convention, transition metal atom has incomplete D subshell, or it gives cation with incomplete D subshell, and they exhibit properties between those of S block element from group number 1 and group number 2 and P block elements from group number 13 to group number 18. The transition elements of the modern periodic table appears as group number 3rd to 12 or as 4 long periods, period number 4 to 7. Okay, and the n-1 d orbital is successively filled in each of these elements, where n is the valence shell. The 3D series of these elements from scandium atomic number 21 here to zinc atomic number 30. Then 4D series is from ytterbium atomic number 39 to cadmium atomic number 48. The next series is 5D series from lanthanum atomic number 57 to mercury atomic number 80. Without those from cerium to lutetium, these are A block element, and last D block element is 6D series from actinium atomic number 89 to curium atomic number 112, without those from thorium to lawrencium. Okay, here it is a second A block series, so these elements are excluded. Then the general electronic configuration of this D block element is, we observe the element, their last electrons entered in n-1 d orbital. Here 1 electron is entered, and in the last element 10 electrons are entered in n-1 d orbital, while the s orbital of that particular period is completely filled. So the electronic configuration of this transition element become n-1 d1 to 10 and ns1 to 2. Okay, so here are the elements and these are the 4 series. But if you observe the periodic table carefully, scandium to zinc is 3D series, but they are placed in 4th period. Then ytterbium to cadmium, this is a 4D series, but period is 5th. Lanthanum to mercury present in 6th period, but 5D series, and from actinium to curium they are placed in the 7th period but 6d series. So here we can again see, because their valence electron entered in penultimate shell, not pre-penultimate, it is penultimate, last but one. So the series number is less than 1 than the respective period. So 4th period 3d series, 5th period 4d series, 6th period 5d series, and 7th period 6d series. Next is electronic configuration. As I said that the general electronic configuration is n-1d 1 to 10 ns 1 to 2. So here 3d series means n-1 is 3. So 3d series from scandium to zinc, the electronic configuration is argon 3d 1 to 10 4s2. Okay, so we'll see again the periodic table and how the electronic configuration of these elements can be written. See here, scandium is here, atomic number is 21. If you observe the electronic configuration of calcium, it is present in 4th period and S block element, but group number is 2. So calcium is 4s2, argon 4s2. Next to that is scandium, and the one electron is entered in 3d orbital because it is a d block element. So the electronic configuration of scandium is argon 4s2 3d1. Then titanium is argon 4s2 3d2. Vanadium argon 4s2 3d3. Then we'll see first manganese argon 4s2 3d5. Iron argon 4s2 3d6. Cobalt argon 4s2 3d7. Nickel argon 4s2 3d8. Then lastly we see the zinc argon 4s2 3d10. Okay, now we have to see the electronic configuration of chromium and copper. As per our sequence, we expected that chromium is argon 4s2 3d4 and that of copper is argon 4s2 3d9. So if you observe the atomic number carefully, 21, first 2 these electrons are entered in 4s, and the next number 1, that electron entered in 3d. Similar for another element except chromium and copper. Why this happen? Why there is exceptional electronic configuration of this copper and chromium, that we have to see. So here is the electronic configuration of chromium. Our expectation is argon 4s2 3d4 because atomic number is 24. But if you observe the 4s orbital, there are 2 electrons, one electron in clockwise, another electron is anti-clockwise. So it has a capacity of only 2, so it is completely filled. But 3d orbital, there are 5d type of orbitals. Out of that 5d orbital, 4 contain one unpaired electron and 5th is empty. So 4s orbital is completely filled and 3d orbital is incompletely filled. Capacity of d orbital, there are 5d orbital, 5 into 2 10 electrons, so it is less than half, so it is incompletely filled. But if one electron is promoted from 4s orbital to 3d. Their energy is nearly same, and due to interelectronic repulsion, the one electron from 4s is promoted to 3d. Then our electronic configuration become 4s1 3d5. Now the 4s orbital is half filled, capacity of 2 electron, and that of 3d orbital capacity is of 10 electron. Now it is 3d5. So 5 electrons are there in d orbital, so 3d is also half filled. So there is a stability order. Incompletely filled atomic orbital are less stable than half filled atomic orbital. Half filled atomic orbitals are less stable than completely filled atomic orbitals. So most tables are completely filled, then half filled, and then incompletely filled. So initially, as per our expectation, 3d orbital is incomplete filled, and it gets converted into half filled, that is more stable. That's why chromium acquires the electronic configuration as 3d5 4s1 and not 3d4 4s2. So this is the reason behind this electronic configuration. Similarly, we can explain the electronic configuration of copper is 3d10 4s1 and not 3d9 4s2. Here also, if you observe, 3d9 is less, one electron less than completely filled. Completely filled is 3d10, so it is incompletely filled. As 4s contain 2 electron, it is completely filled, but the 3d is incompletely filled. One electron from 4s is promoted to 3d due to interelectronic repulsion between these two orbitals. Our electronic configuration become argon 4s1 3d10. 4s is half filled, 3d is completely filled. So incompletely filled electronic configuration gets converted to completely filled electronic configuration. That's why copper acquire this absurd electronic configuration. So when question is write the electronic configuration of chromium and copper, write down always the observed electronic configuration, not the expected. And there are questions why the chromium and copper shows this electronic configuration as a observed electronic configuration. You have to write the explanation or the reason behind this observed electronic configuration. So this is about the electronic configuration of chromium and copper and the remaining electronic configuration of 3d cells. So one electron in first element in 3d orbital and last element contain 10 electron in its 3d orbital. That is from scandium 4s2 3d1 and zinc argon 4s2 3d10. Okay. In this way, you can write the electronic configuration of 4d, 5d, 6d elements. Okay. So here is the electronic configuration of this element. Always write down this electronic configuration for chromium and for copper here. Okay. Then oxidation state of first transition series. The loss of 4s and 3d electrons leads to formation of ions. So loss of one electron from 4s orbital electron and it forms 1 plus ion. So it is represented by M1 plus ion. If 2 electrons are lost from 4s orbital, then it forms M2 plus ion. While loss of unpaired electron from 3d and 4s electrons combinedly, it forms M3 plus M4 plus ion and higher cations of the respective elements. So let us see the elements and respective cation with loss of one or more electron from the 4s and 3d orbital. So element, outer electronic configuration, oxidation state. So first scandium, it contains 2 electrons in 4s orbital, 1 electron in 3d orbital. So if it donate 2 electrons from 4s, then it forms +2 oxidation state. It does not donate 1 electron because if it is empty, then it is more stable. That's why it is +2. And if it donate one more electron from 3d orbital, then it forms Sc3+. Similarly, the remaining element also donate 2 electrons from 4s orbital and 1 electron from 3d orbital. So they form 2+ and 3+ cations. If you observe titanium, 3d contain one more electron because electronic configuration is argon 4s2 3d2. So if it loses 4th electron from 3d orbital, it forms 4+, titanium 4+. In case of vanadium, there are 5 electrons. So the 5th electron from 3d orbital, if it is donate, then it forms vanadium 5+. In case of chromium, there are total 6 electrons, so it can form +6 oxidation state. While in case of manganese, total there are 7 electrons, so manganese can form +7 as a highest oxidation state among these transition elements. So if we go from scandium to manganese, all these elements, they show +2 and +3 as a common oxidation state, but from scandium, if we change to next titanium, it shows +4, then vanadium +5, chromium +6, and manganese +7. So if we go on increasing the atomic number by one number, their oxidation number also increases with extra one. So +4, +5, +6, and +7. So manganese shows +2 to +7 oxidation state. So on adding one electron in the penultimate shell, last but one, not outermost shell, so oxidation number increase by 1 unit. And then again from iron to zinc, the oxidation number decrease by 1 unit. The elements which gives the greatest number of oxidation state occurs in or near the middle of this 3D series. Manganese element, for example, it shows oxidation number from +2 to +7. Well, in case of Fe, again oxidation number decrease, one oxidation number decrease, that is +7, and it shows +2 to +6. Then cobalt shows +2 to +5, nickel shows +2 to +4. Then your copper shows +1 and +2, and zinc shows +2 only, because in case of zinc, that electron from 4s orbital is removed, and it is very difficult to remove the electron from 3d orbital because 3d is completely filled. So it is very difficult to remove the electron from 3d orbital, because after loss of 2 electron, Zn 2+ electronic configuration become argon 4s0 3d 10. So here is the electronic configuration and the corresponding oxidation state of the cations from the transition element. Next is the electronic configuration of various ions of 3D elements. So see the scandium electronic configuration is, every time you have to write argon first, then 4s2 3d1. If it loses one electron, then the electronic configuration of so write down the element Sc, and charge is 1+, 3d 1 4s 1. One electron from 4s is removed and it forms M1 plus. If we remove one more electron from 4s, 4s contains 0 electron and our electronic configuration become 3d1 4s 0. So here one electron, make it correct in your textbook also. Okay. Okay. Wow. Not 2, it is 3d1. Okay. Then when it loses one more electron from 3d, then electronic configuration become argon 3d 0 4s 0. So it is Sc3 plus. So in this way we can write the electronic configuration of that element in its 1 plus 2 plus and 3 plus. Okay. So similarly you can write the electronic configuration for titanium. Titanium is 4s2 argon 4s2 3d2 when it is in metallic state. When it donate one electron from 4s orbital, the element becomes now cation. Ti1 plus is argon 4s1 3d2. When you donate one more electron, then Ti2 plus electronic configuration becomes argon 3d2 4s0. Okay, and for Ti3 plus it becomes argon 3d1 4s0. So in this way you can write the electronic configuration of the 3d elements. Okay, now next is, if you observe the electronic configuration of zinc, Zn1 plus is argon 4s1 3d10. You can't remove the electron from 3d orbital because it is completely filled, and in case of Zn2 plus argon 3d10 4s0. So 3d orbital is completely filled and there is no electron from 4s orbital. So most stable for zinc is Zn2 plus. So in this way you can remember the cations of the respective element. Zinc always shows Zn2 plus. Okay. Then next is physical properties of first transition series. So there are different properties shown by this transition element. It shows first metallic properties, and there are different properties of metal. So malleability, then ductility, then this element, they shows luster, shiny appearance, they are hard and they can form alloys. Detail about how they form alloys and which element shows which alloys, that we'll discuss in the next part. Then second physical properties, they have high density and their melting point and boiling point is also higher. The reason behind this is due to metallic bonding. Then next properties, they are good conductors of heat and electricity. Then they exhibit variable oxidation state from +2 to +7. Then they form large number of complexes. So in coordinate chemistry, we'll see the central metal atom is transition element. Okay, so there are various complexes K4 APCN6, K3 APCN6. So these are some examples. Then they shows catalytic properties. Most of the transition elements, they are used as a catalyst in various chemical processes. So all are familiar with hydrogenation, nickel, platinum, palladium. They are used as a catalyst for hydrogenation of unsaturated hydrocarbons such as alkenes and alkynes. They can be converted into saturated hydrocarbons, alkenes. Then they can also form organometallic compounds. Thank you for watching my YouTube channel, KHARGE.